Hello, my name is Jason Davis, and today I'll be presenting CLES, a universal wrench for embedded systems communication and coordination, a paper written by myself and Dr. Tilevich. So we're going to follow some of the waterfall procedure to go through this paper. First with an introduction, going through our problem domain, competing existing solutions, how we apply RESTful architecture for embedded devices, our evaluation of CLES, and then our conclusions. So first, this research effort contributes CLES, the communication language for embedded systems, which is a RESTful architecture domain-specific language for embedded systems communication, as well as a standalone CLES runtime for managing distributed computing tasks, an evaluation of CLES with representative micro benchmarks and realistic case studies. And incidentally, CLES means wrench in French. So CLES is designed to be a universal wrench for solving embedded systems communication. So first, let's talk about our problem domain. We're primarily targeting automotive and defense industries because of their large-scale decentralized computing systems. Properties of these distributed embedded computing systems are dynamic connectivity graphs, heterogeneous systems, real-time operating systems, low-power devices, decentralized communication, and high reliability and limited bandwidth. So first, let's talk about the specific example of vehicle platooning. A vehicle platoon is a group of vehicles autonomously following a leader using inter-vehicle communications. The purpose of a platoon is to increase highway safety and reduce vehicle fuel usage. Some of the challenges in vehicle platooning is the wireless protocol, which is solved with either 5G or 802.11p, the control algorithm for each vehicle, which is solved. One dominant example is the constant spacing strategy. And then there's still the software middleware problem, which is an open problem of how to actually implement this on a large scale, in which we're going to propose CLES. The second problem domain that we're going to explore is JDAC, or Joint All-Domain Command and Control. This is primarily an investment of the US military, but it's also being done internationally. And the goal is for cross-domain heterogeneous coordination between air, land, sea, and space. So we're going to focus on a JDAC subset of a distributed sensing network, where we have satellites, reconnaissance aircraft, strike aircraft, and then a command and control C2 cell. So let's talk about what's common in these problem domains. So all of these problems have heterogeneity requirements, being this different purposes in each device, different operating systems, different languages. There's also competing companies developing these different platforms, different automotive manufacturers and defense contractors in countries. They also have a strict security requirement. Vehicle platooning specifically has a low latency and high reliability requirement to control the vehicles, whilst the JDAC sensor network is more focused on decentralized task management between the nodes and asymmetric capabilities where each device has a different purpose, specialized hardware, and then, again, a loosely connected communications graph. So let's talk about existing solutions to solve this problem. So going back to some of the original solutions, there are custom data link layers that actually define the structure of the data itself, such as MADL, the Multifunctional Advanced Data Link, Link 16, and a handful of others. These are non-heterogeneous, non-extensible, expensive, they can't communicate across data links, and they only solve the problem of data structure. There is no semantics. Next, we have transmission packet defined in a strict ICD. This is similar to the data link layer, except it's cross data link, but it's still non-extensible and inflexible. At one level higher, we have Google protocol buffers. This is effectively a generated ICD, which has some of the same requirements where it's a strict data structure, it's not backwards compatible, there's no middleware to actually define where the data is going. It's purely a generated one-step higher ICD. Next, we have more of a distribution service. We have products like ActiveMQ and DDS. These are the opposite problem, where they're purely middleware. They don't define the actual data itself, only its distribution. Additionally, ActiveMQ requires a centralized broker, which breaks our decentralized requirements. And then both of these have very high bandwidth requirements for synchronization between the nodes, which is incompatible with JDAC and strict military data links. So next, let's talk about the most dominant solution for distributing tasks, which is container orchestration. This is the idea that one or more manager nodes can distribute tasks across a collection of worker nodes. And this is a one-to-one execution where a container is designed to execute a specific task. Kubernetes, being the dominant solution, is what we're going to explore. The problem with Kubernetes is it requires specific operating systems, and in the case of embedded systems that run real-time operating systems, like aircraft, you would require a special additional computer just for running Kubernetes. Kubernetes is also centralized, where you can still have a limited set of Kubernetes master nodes or manager nodes. It's still effectively a centralized control system. Because of this, it's a single point of failure with either one or a small number of hosts. And then container deployment itself has a huge bandwidth cost. When you request a task from a Kubernetes server, it actually deploys the entire container to another device, which would overwhelm low bandwidth data links. So next, let's talk about how we are looking at RESTful architecture to solve this problem. So first, let's talk about CLES. So what we're presenting is the CLES software development kit, which is a C++ development kit. This includes both a point-to-point CLES service interface, similar to the Java Net HTTP package, and then a CLES runtime application, our API, which is designed to be a standalone runtime that distributes tasks across devices. This is extensible with C++ plugins to allow for asymmetric capabilities. So the requirements for designing CLES are, of course, this distributed and networked components. So we can't use anything that's within an OS interprocess communication, such as shared memory, OS messaging, semaphores, memory mapped I/O, etc. We also require heterogeneous coordination, so we can't use, again, OS or data link specific device-to-device communication, such as QNX Neutrino and AIDL. Next, it must be decentralized, so any of our task allocation must be asymmetric. And then our programming language restrictions. Defense and automotive industries have very tight programming restrictions, but C++ is common across both these industries and can compile on nearly all OS and hardware within those industries. So now let's design the actual language for CLES itself. The CLES language, it follows the RESTful architectural style, where it has a limited set of verbs that define the semantics, and then a limitless set of nouns or modifiers, which define what these verbs are being applied to. This language is also plain text, which makes it easily portable, and it abstracts the backend functionality from the interfaces, which can also help protect classified and proprietary information. The 5 verbs that we've chose to go with are pull, push, delegate, bind, and update. This is a similar but different subset of what you would see on the internet with HTTP. Primarily, pull for getting data, push for sending data, and then delegate is really the send parameter get result, which is what's going to do your task allocation, and then bind and update is a register for persistent updates. So here's a quick look at the grammar. It's very simple. You have a verb and a noun, and then your noun represents your target, your task name, and any additional parameters. Everything else is generic strings. So now let's look at the response structure. So CLES is primarily a RESTful architecture for the requests, but for the response, we've decided to go with JSON because its layered key value mappings and plain text format allow for a high amount of flexibility and expandability while still being completely data independent. It breaks some of the restrictions that we had with ICDs. Next, let's look at a quick example. So we can have a request for bind to another vehicle's localization data with the units, SI units. What this would do is your target vehicle would request all localization data from another vehicle using those specific units. And then we also have an example of what's tied to this JSON package on the right, which is you could post to all vehicles in your system the hazard packet, which would have that structure, which could contain required fields such as type and lanes for blockage and all, location, but you can have additional backwards compatible fields added later, such as cause for more advanced systems. So let's look a little bit more at the software side behind it. So the CLES point-to-point service integrates directly into a parent application. This service manages your network interfaces to other CLES applications. It handles CLES language parsing and interface application of the function. And then it's also designed for minimal data hops, directly from application to application. This is specifically to minimize latency and give you deterministic real-time performance because it can be called in line with a parent application that is running on a real-time operating system. And then for the CLES runtime, we focused on the design philosophy of a distributed collection of thread pools. So in the same way as the thread pool can function, each runtime can make and handle requests functioning as either a manager or a worker node. This allows for that decentralized task management. Each runtime is able to register applications loaded on startup that are individually developed using the SDK. This solves the asymmetric capabilities and high bandwidth cost of container transfer. The runtime can accept requests from devices running only the point-to-point service, which allows for lightweight edge nodes, for example, cheap remote sensing devices. And then the primary interface for this runtime to get its full capability is using the delegate verb to delegate a task to a specific remote CLES runtime. In terms of the actual implementation details, this was developed in C++ 17, which stands for Automotive Defense and Embedded Systems. using no third-party library, so all source code is available for safety and security certification. For communication across devices, we used OSI IP, which is compatible for nearly all modern data links, Wi-Fi, 5G, Bluetooth, most military data links. They also have your traditional IP flexibility between UDP and TCP, whether you need latency or reliability. And it's also extensible to protocols such as RTP for more real-time reliability and latency. The abstraction from the user of CLES allows for extension of other data distribution platforms in the future, like ActiveMQ and DDS. The build process was also done on CMake to make it easily cross-platform. And then the only thing to port CLES to another platform would be to swap in the networking system calls. Everything else should be standard C++. The CLES C++ static library is easy to integrate into a parent application, and then for the point-to-point service. And the CLES C++ dynamic libraries are created by a user for the runtime application extension. So let's talk about our evaluation of CLES. So first, does CLES meet our timely requirements for vehicle platooning? Is the plain text packet structure of CLES compatible with network protocols for embedded systems? How does this affect the developer workload compared to traditional programming models? And then does CLES provide the simple support and flexibility for distributed processing tasks? So first, to evaluate the point-to-point service with a focus on low latency, we set up 2 applications using the CLES point-to-point service and 2 applications using a serialized ICD to test the round trip of a CLES pull request and response, similar to what you would see in vehicle platooning. What we notice is that CLES adds about 1.5 milliseconds of round-trip overhead. This is a fraction of the 100 millisecond requirement for vehicle platooning, and this also represents the worst case because we're using a round-trip bind and pull, which is a request and response, whereas a bind and update could effectively increase performance. Also, the CLES parser itself is effectively O of 1 because the language has a strict requirement on the length of the request. So even though it's a linear processing parser, the requests are restricted to only one verb and a few nouns. The packet size, being plain text versus a traditional ICD, CLES was about 132 bytes, which is 3 times larger than the ICD, but this is insignificant relative to, most importantly, your 1500 byte MTU on 5G and Ethernet. In terms of workload development, it was about 30 lines of code to develop the CLES solution, versus 10 times more code with 300 lines for the traditional solution. Next, we evaluated this distributed processing using stochastic gradient descent. So we created a distributed machine learning algorithm using the baseline of stochastic gradient descent, but parallel to stochastic gradient descent distributed across different nodes. We set up 2 nodes, each with a CLES runtime, and then each runtime running a custom stochastic gradient descent capability. And then one node delegates the SGD locally and remotely to the other runtime. And then this was a simple classification of 2 data sets of 100,000 points each. The algorithms we used are below. So the most important thing to note is that the additional CLES overhead of comparing locally versus actually using CLES to command it is only about 100 milliseconds, which in terms of these representative large distributed machine learning training tasks is fairly representative because the primary usage of your time is actually calculating each individual subset of the application. The most important thing is this CLES application only took about 300 lines of code, and this is a completely reusable design pattern for any target domain that requires a management node, and then a divide and conquer, and then consolidate semantic solving. So, and then lastly, we did our quick case study. So we looked at the vehicle platooning, and the paper goes in more detail about using CLES to actually implement the point-to-point vehicle platooning solution because it supports 802.11p or 5G with OSI IP. It's directly integrated into the vehicle control module. Using the localization capability with bind allows for a low latency bind and update paradigm. Then each vehicle only needs to bind to the vehicle it's directly following, and the lead vehicle following the constant spacing strategy. Lastly, we looked at the case study for JDAC, which the CLES also meets all the runtimes for JDAC. It's flexible across multiple operating systems, it's quick and cheap to integrate, and has multi-data link support through OSI IP. In terms of each individual device, we can use a variety of both the runtime and the individual point-to-point service, depending on if, for example, the satellite is accepting delegation tasks for processing video feeds. Reconnaissance aircraft can send a video feed with just the point-to-point service. The command and control node is able to bind to all target tracks from the other aircraft. And then this command and control, which would typically be your officers, can send a strike task to the strike aircraft using the CLES runtime to execute a strike from the data provided by the satellite and reconnaissance aircraft. So, a quick overview. So, our modern embedded systems are increasingly heterogeneous and distributed. The existing solutions like ICDs, data links, and protobufs are inflexible, coupled with wireless protocols, difficult to extend, and expensive. Modern software solutions such as ActiveMQ, DDS, and Kubernetes have limited operating support, OS support, heavyweight middleware, no timeliness requirements or guarantees, and no data definition itself. CLES solves both of these problems, though this specifically because the RESTful architecture is flexible and simple. It has nearly limitless OS and data link support through the C++ standard and OSI IP. It meets latency requirements using the point-to-point CLES interface directly in a parent application, and it meets the decentralized task distribution requirements using the CLES runtime. Most importantly, CLES is the baseline for a realistic middleware solution for the most challenging aspects of heterogeneous networked embedded systems.